talk about a problem. This problem is the difference of the values of the quadratic equation is a constant. So first, let's draw this. So first, let's draw a picture and imagine this problem. So first, we draw a quadratic equation, and this equation is x squared. Okay, just talk about this equation. This is x squared, and we see now, and we choose some x values. And of course, the interval of every two of the x values, they are the same. And so we have a y value, right? So now, because we know the difference of difference, so first we find the difference of the values. So we find the difference of this one, and this one. So what's the difference? Draw a line here. This is the difference. And this one is this. So what's the difference? Draw here. So this is the difference. So now you need to find, actually you need to prove this difference and this difference. The difference of these two differences are a constant. So now this is our aim to. This is our aim. Okay. So first, let's see how do we think about the problem. So first, because we have the difference and these two differences, so what we do is, let's think, because every values, even these difference, that creates by, you see, this difference is from start from this point, and the first increment is the first dy over in this point, and we use the dy over dx times the derivative times dx. So we can get an increment here and increment. Every increment is get from the dy over d. In this moment, we use the dy. In this moment, we use dy over dx. The dy over dx of this moment, and then times dx, and so on, and we can just calculate out. So now, this difference is the same. First dy over dx times dx, and the second dy over dx times dx, like that, so on. So we find first we have a way, and we have a solution to prove this problem. Is we can find first we find the difference of the first increment of this difference and the first increment of this difference. So, and then the second time is we find the difference of the second increment of this difference and the second increment of this difference. So, and then so on. So this is our solution to think of this problem. So now we need to prove it. We will draw the differential function. Okay, what's the differential function of a cos? Of course, you know that. That is 2x, right? 2x. So let's say 2x, and then what? We draw the same x value. So what? Because we know in the differential function, we need to think about the area, right? So these two difference right here is these two difference, but it's the area difference, right? These two area difference. So what's that now? So we use this area minus this area. So what we got is we can move this to here. So what's that? Okay. So now the area we are thinking, we are calculating. We are proving it. We need to prove it is a constant. Is this area? It's just like what it calculates look like. Okay. Like here, and what we do is the first increment right here is the first very tiny rectangle. Okay, very tiny rectangle. It's very tiny and long rectangle. And we know because then what's this value? Because this function is 2x. So this is 2 because why this is 2? Because we know this difference is 1. Okay. This difference is 1, so that's why this is 2, right? Get mad at that, right? So let's see, because that's this is a linear equation. Okay, so that's why it's 2. That's why this one is 2. So each of them is 2, and in the first increment right here, it is an area. It is small and long area, and this area is 2 times dx. Right? Okay. So right here, just the equal with dx times dx, and that's fine. We can project it here. So this is dy over dx. The slope right here, right? And this is the value right here. No. I mean, right? Because we find the difference of these two slopes, then times dx, right? Yeah. Because we use this increment to minus this increment. That's equal to, we use this in the slope in this moment to minus the slope in this second, and then times dx. So the difference of these two slopes are 2. Right here is these two slopes. The difference of these two slopes, right? It's here, 2. Right. Okay. So first, yeah, this one minus this one is this one. So actually, can use this one minus this one, right? Okay, it's this one. Okay. So anyway, so we know because here in this area, in this part is 2dx and 2dx, because and how many of them? Because we know this is 1, so 1 times x. 1 divide dx. This amount, what is the amount of 2dx? It is 1 over dx. 1 divide dx. This amount of 2dx. So actually we can write down in a row. So in a row, and we said this is k and this is k plus 1, okay? And so k to k plus 1. So, and of course, let's see here. So, what's that? That's 2 and then dx, right? So, let's see. So, what is the range of k? So, first, k, we know that's a positive integer. That we can say k is the member of the positive integer, right? So, and there's another condition. So what, if you think about, if k is 1, so what's the difference? So what is the difference that is going to minus by the difference right here? So what's that? None of them. So k can't equal to 1. So k needs to be greater than 1, right? Okay, so we just find and grow, and we know that's equal to we don't need to think about it. Equal to. Actually, that's equal to 2. That's equal to 2. So first now so actually we have this problem. So we actually, because now because we know this part is 2, because right here just the slope minus the slope and then times dx and so on, blah 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 blah. And actually this is we find the difference of this pair of this pair of slope and then times dx. And how many pairs? It is 1 over dx, pairs of them. So actually, in every pair of them, the difference in times dx, and that's 2dx. So actually, we can write out. Oh, we don't integral. So if we don't write integral, so that we can write 2dx. We have many ways to explain this, right? So, and then 2dx times what? 1 over dx. So what's that? I think that's equal to 2, right? Okay, so this area, is what? Is 2, right? Okay, so it's 2, and then this part is 2. So this one minus this one is 2, and it's a constant because each of them, if we use this one minus this one and this one minus this one, they are the same. This one is this are the same because just right here, right? It's easy. So let's use the other word to prove it now. Okay? So first now I said this is called xk, and this is called xk minus 1, and this is called xk minus 2. Okay? Okay. So yk, I mean right here, okay? Yk, this is yk. This is yk minus 1. And yk minus 1. And then of course, and this is yk minus 2. Okay, so, and what's the secret to do? Let's keep going on because we set this function because we need to prove each of the quadratic. So we use ax squared plus bx plus c to explain that. So first, right here, we plug in the x. Okay, so it's a times xk squared, and then plus b times xk, and then plus c. And then minus ax minus 1 squared, and minus b times xk minus 1, and then minus c, and c would be cancelled out. So, and what's next is we can these two parts. These two parts, so what we can change them to is we can factor out a, and then inside this part we can change it to a times, and because we can change it to and of course let's set here, set x xk minus xk minus 1 is equal to n. This is here. Okay, that's not equal. Okay. Okay, this is for what we set. Okay, this is for what we set, and let's see. A, and then what? Let's see. And m, right? Because xk to the 2 minus xk minus 1 to the 2, and that's equal to x bracket xk minus xk minus 1, and then bracket times xk plus xk minus 1. So, and part of xk minus, in these two parts, one of them is xk minus xk minus 1. So this is m, right? So am, and then times bracket xk, and then plus xk minus 1. And then, you know what? You see, because xk minus xk minus 1. Yeah, because in these two parts, we can factor out b plus bn, right? And they're equal to a what? Am times inside is, right inside is, we can change it to xk minus xk minus 1, and then plus 2 times xk minus 1. So that is, so the front part is m. So that's m plus 2 xk minus 1. And then plus bm. Okay, and then equal to what? And this part we can times it in. So an squared an squared and then plus 2am and then times xk minus 1 and what? And plus bm. And now what we need to do is we use yk minus 1 to minus bracket yk minus 1 minus yk minus 2 bracket. So now what's this equal to? We can just plug the things that we've proven, because yk minus 1 minus 1 yk minus 2 is the same. We can just plug in this function in. Am squared and bm squared are cancelled out. So we only left 2am and then times xk minus 1 and then, minus 1 and then minus 2am xk minus 2. Okay, very perfect. So, let's see here. So that's equal to, because we know, before this problem, I talk about the interval of each two of x values are the same. So xk minus 1 minus xk minus 2 is what? Is m2, right? So what's that? So that is 2am squared. Because on here we can factor out 2am and inside is m, so that is 2am squared. So, and this is our constant, right? Okay. And so now we can extend this problem to the difference of the difference of the difference. Sorry. Before this problem, first we say, of course, right here, we know. Actually, before this proof, in this picture, we know these difference are what? These difference are arithmetic progression. Okay, they are arithmetic progression. Okay, so let's keep on our problem extending this problem. And we can think about this problem is the difference of the difference of the difference of the values of the cubic equation. So now we need to draw out the cubic equation and it's more faster than it. Okay. And of course it's the same, this is xk and this is xk minus 1. Actually, I can send it later. I just send it now. Okay. And first, we know we're C, because now what we're going to do is to prove this minus this, so we can get a difference. Sorry, first we use this value minus this value. Of course, these guys, the interval of these guys are still m, okay? This step is never changed in this problem. Okay, which we use this one minus this, and we got which we got this, and we use this one minus this one, in which we got this difference, and we use this minus this, and in which we got this difference, and we have these three difference. So using the first difference to minus the second difference, so we can have a new difference of difference. And using this difference to minus this difference, we have a difference of difference. So now the second step is we need to draw the what? the differential function of this function, differential function of the original of course, this is x to 3, okay? So the differential function is 3x squared. Okay, so 3x squared, so let's draw the things. Okay, and then let's draw here, here, and here. So what we're gonna aim is not this. Sorry. We don't need here. Of course, from this step on, let's see. So we proved this problem, right? Before, right? We proved this problem before, so actually we can think about this whole problem of the quadratic equation is a landmark for when we are extending to the cubic equation. So let's see here. So first, because these are different, so we are thinking about this area and this area and this area. So this is a little bit hard, but actually the same. And now we use this minus this. Is equal to we use this area to minus this area. So we can move it same right here and then okay. And so we need to find an area right here, right? So actually, I'm going to draw it right here too. And we use this one minus this one. So now actually we're calculating this area and this area and so on. Right? So actually these areas are arithmetic progression. We need to prove this. And so actually we need to prove this part minus this part is constant. Okay, very good. So we need to prove it's a constant. So what we do here is this part minus this part. And what's that? So first, right here, because we had this left. Don't forget. And first, we had the first time, and we use this value to time dx, and minus, right here, we use this value to minus time dx. So we have two little areas. Right, two little areas, and when you find their difference, and we can find the two values, the difference of these two values. Okay, so we draw the differential function of this 3x squared function. Alright, linear equation. Okay, this slow. It's a bit faster because this is 6x. Okay? Okay, and this is 6x. So now what we do next is let's see okay, and first we draw like this. Actually, that's very easy. Okay, so first we know because actually we don't need to draw it clearly because 6x. So what we do is, you see, because we are calculating these two values, the difference of these two values. So right here, what's that? We just move this right here, and that's something like the same, you know. Like this, and we're calculating this element, and because we have this lemma, so we know this part of area is 6. Because right here, if we have a small and long area, and this area is 6, the x, because the slope, the difference of the slopes, right here, this is 6, and then times the x, and then times the x. Right? Okay. So we know that, right? Okay. That's 60x and 60x, and so on. So what's that? And that's how much? And what's the amount of them? It's a 1 over dx. This amount of them. So we know here. So this is the same pairs. This because we know this value minus this value, this value minus this value, this minus value, this value minus this value, and so on. So how many of these pairs of finding the difference of this pair of values? How many pairs of them? 1 over dx pairs of them. So and this one is this. It is 6, 6, 6, 6, 6, 6. Now each of them times their dx. So what's that? 60x, 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 and so on. So what we do is, so how many of them we just say it's 1 over dx of them. So what's that? It is 6. Okay, so we know this part minus this part is 6, and that's a constant because all the time we know even this part minus this part is 6 too, right? Actually, now we can write out the integral. Sorry. We can write integral, and then what's the integral? So first, let me think. Integral and then 60x. 60x. And of course it's k to k plus 1. And k has the same range. K is the member of positive integer, and the k is greater than 1. Okay, that's fun. And we know it's 6 because we have another way to explain it, and that's 60x times 1 over dx, and that's equal to 6. Right, okay, very perfect. So we have proved this problem using pictures, and now we need to prove using algebra, just like the coordinate equation. Actually, this is simple, but you look at this. Sounds like very hard. Actually, that's simple. And first, let me write here, that's yk minus yk minus 1. And the set is the same, okay? No change. Touch again. Okay, and first, let's see here. And first, this is equal to, we know, and this function changed to ax k to the 3, and then plus bxk to the 2 plus cxk, and then plus d. Okay, and a minus ax k minus 1 to the 3, and then minus bx k minus 1, and then to the 2, and then minus cx, and then cx minus 1. Okay, and then minus d. So d is going to be canceled out, and we don't talk about this part, this and this, because this and this, because we talked about this before, right, on the quadratic equation. And so now we are going to talk about is, what about this part and this part, right? And so, now what are we going to do? And let's do this next step, right? So it's equal to, let's see. Okay, you can see this, okay? You can see this alright, and these two guys, and so first we can factor out A, and then let's see next step, and we can just take out a part like M, and inside we can find out that is xk squared, and plus xk times xk minus 1, and then plus xk minus 1, and then d2. And then plus b, and we factor out b, and then times, and then this bm, and then it's bm, and then times bracket xk plus xk minus 1. Okay, and then plus cm. So now we have this function, and we can plug in the function if we just change it to yk plus 1, k minus 1, yk minus 1, and then minus yk minus 2. So what's that? Of course, I already hit minus, okay? And this is not equal to about something, like equal. And first, we just plug it in, and I don't know about it because you know how to plug it in. It's 2, and then plus xk minus 1, and times xk plus 2, plus xk minus 2. And then plus bm, and then bracket and then times bracket x k minus 1 plus x k minus 2. Plus cm. Okay, and the next step, of course, we're just putting together. So now we're in here. This part is okay, and let's see. We right here. Of course, I already here because and I have some places, and we don't have much places to write this. And am, and then see here, and then this minus this, and these two guys are being canceled out because this part is negative. So xk to the 2, and then plus xk x times xk minus 1, and then minus xk minus 1, and then times xk minus 2. And then next, and what's that? Let's see here. Minus x k minus 2 to d2. Okay, and then let's see the next step. And then plus 2bm squared plus 2bm squared. And why is that? Because we can just factor out 2m, and this minus this is equal to m. This minus this is equal to m. So 2m times bm, 2bm squared. So the next step is we have a new function. Yeah. So first, next step what we are going to do is change it again. So A is not changing, and then changing the bracket inside is okay, and this part is so first let's see these two parts, because these two parts we can use the same way, because that is xk minus xk minus 2 bracket times bracket xk plus xk minus 2. And 1 minus 1 plus, and the minus part is 2m, right? Because it's xk minus xk minus 2. It's not minus xk minus 1. So that's 2m. And then times bracket xk plus xk minus 2. Right, okay. And then now we think about these two parts. This part. Plus, and we can factor out xk minus 1. And then xk minus 2m. So 2m, what? 2m times xk minus 1. And then 1. Bracket, right. Okay, and then plus 2bm squared. So now, and we times it out. Okay? And that's equal to, first this part times out, and we can get 2am squared, and what? And then times bracket k xk plus xk minus 2. Yes, that's right. Plus, yeah, you see, it's still 2am squared, and then 2m squared, and then times, okay, xk minus 1, and then plus 2b squared. Sorry, 2bm squared. 2b times m squared. And then, so, the same in another part, right? Because what are we calculating right here? There's this part. Right, now we are just using the same function to plug in, and then we find out this part. The area of this part. First we find out area of this part. Now we find out. And this part, we just plug in this function, that's fine. And then minus what? 2am squared. And then times okay, times bracket xk minus 1, and then plus xk minus 3, and then plus 2am squared, and then times xk minus 2, and then plus 2bm squared. So we have a lost answer now. Lost answer. So what is the lost answer is, let's think. This part, this minus this minus this. And all they are 2m. 2m right here, 4m to be 3. Wait, what's here? And we use this minus this and this minus this. So that is, yeah, that's right. Yeah, that's equal to, no, it's 2, sorry, that's 4a 4am 4am to these 3, and then plus, let's see here, this is m, so plus 2am to these 3, so actually that's equal to 6am to these 3, and this is a what? A constant. Am I right? A constant. Okay, so we have proved this problem. Yeah, we have talked about it. So we have talked about this from problem. Fun problem. Actually, we can find out. First, we prove. We use an image to prove the difference of the value of the quadratic equation is a constant, or you can say the difference of the quadratic equation. Sorry, or you can say the difference of the values of the quadratic equation. And then we use algebra to prove it. And next we extend this problem to find the difference of the values of the cubic equation. Or you can say we need to prove, or you can say we extend it to the problem like finding the difference of the values. Sorry. We are going to prove. Sorry, right here. Sorry. Or you can say right here we have two things to prove. Actually, they are the same things to prove, but we can use two things to say to explain this. You can say the difference of the values of the quadratic equation are a constant, or you can say are constant, or you can say the difference of the values of the quadratic equation is a arithmetic progression. And right here we extend, and then first we use image to prove this problem, and then second we use the algebra to prove it. And then we extend this problem to the difference of the values of the quadratic equation. Of the cubic equation is a constant, or we can say the difference of the values of the cubic equation is an arithmetic progression. And then first we use image to prove this problem, and then second we use the algebra to prove it. Right? So we have solved this whole problem.